This lecture covers the last topic in this unit on work and energy. This lecture is specific to AP Physics C. The topic is referred to as a potential energy diagram. The potential energy diagram is an easy visual means of qualitatively determining what possible motions can occur for an energy system. So let me begin immediately by drawing out a simple potential energy diagram. A nice example of a potential energy diagram is a roller coaster. You could actually think of a roller coaster as a specific type of diagram that describes potential energy. So here's what I mean by that. Okay, so potential energy diagrams. And a nice conceptual example to begin with is a frictionless roller coaster. So, of course, if it's a frictionless case, then potential energy is transformed into kinetic energy and then back again as the coaster train moves along the track. Okay, now I'm going to graph out the coaster track in the following way. Okay, first of all, I'm going to have a horizontal axis that represents position. Let's consider a coaster track that just moves down in one direction. That position is usually referred to as R. And then right here along the vertical axis, we're going to graph out the potential energy as a function of R. Now the potential energy itself, of course, is mgh. However, on this graph, what you want to think of as the height h as a function of where you are here along the axis, that is, along the axis R. So then therefore I can graph out the track of the roller coaster as some sort of complicated function that obeys this expression, that is like so. Let me put a couple of hills in, like this. Okay, and now let's say that I have a coaster train and I give it a certain amount of energy. The energy is conserved, so then therefore we can think of the energy as a constant, as a horizontal line somewhere here on this graph. So for example, let's say that I give the coaster a certain amount of energy. Let's say, using a different color, right here is that total energy E, like so. And then let's simply begin by placing the coaster train right here at this point. Let's go ahead and begin the object at rest. So then therefore, at that point, all of the energy E in green is equal to the potential energy U in red. So here E is equal to U. Now remember, of course, that energy E is kinetic energy plus potential energy. So then therefore, what is the kinetic energy equal to right here at this position on the graph? It's obviously equal to 0. So therefore, the kinetic energy is equal to 0, and as I said, the object begins at rest. Okay, and then let's say that we release it from rest, like so, and then you have the transformation of potential energy into kinetic energy as it moves downwards. Let's go to this point here on the graph, like so. So at that particular position, the potential energy in red is equal to 0, therefore all of the energy E is kinetic energy. Once again, E equals K plus U. So then therefore, how would you represent the kinetic energy K on this graph? Well, the kinetic energy K, here's an easy way of thinking of it, is equal to the energy E minus the potential energy U. It's basically the difference between this value here and this value here. So on this graph, therefore this difference, like so, I'll draw here in blue, that's the kinetic energy K. And then let's say that we begin to have the coaster cart move along the next hill. Let's say that it gets to the top of the next hill, like so. So how would you represent the kinetic energy K then therefore on the graph? Once again, it's just simply the difference between the energy E and the potential energy U. So then therefore here on the graph, it's essentially this distance, if you will, like so. Think of it merely like this. Right here in red is the potential energy, and then plus the kinetic energy in blue. That then gives us the total energy E in green. Okay, now let's say that I take the same coaster with the same amount of energy, but let's say that I talk about this portion of the graph over here. Is it possible for the object, if I give it this amount of energy in green, to be over here on the graph? The answer to that question is no. And the reason for that is because at this point right here, notice that the potential energy U in red is bigger than the total energy E in green. So then therefore, if the potential energy U is bigger than the energy E, what type of number must the kinetic energy be? It must be a negative number. That's of course impossible because kinetic energy is always a positive number. It's 1/2 mv squared. It's just the energy associated with motion. So then therefore, if I give the coaster this total amount of energy E here in green, This then means that this region, as we say on the graph, is unallowed. The coaster can only be on this portion of the graph forward, like so. So by examining the potential energy here and drawing it out as a graph as we've done, we start to get very quickly a qualitative understanding as to exactly what types of motion are possible for a system. Okay, here's another example. Okay, I'm just going to draw the same graph, but let me erase here. Like so. Okay. Let's say that instead, what I do is I give the coaster this amount of total energy E, like so. And then let's say that I start right here at this point. Once again, like in my last example, at that point, the kinetic energy would be equal to 0. All of the potential energy U in blue is equal to the total energy E in red. And then I would release the object at this point, for example. And then down here at the bottom of this well, by the way, as it's sometimes called, down here at the bottom of the well, all the energy would be kinetic energy. Right here, the potential energy in blue is equal to 0. Therefore, the kinetic energy K is the difference between E and U, like so. It would be this distance here on the diagram. And then the object would move from here to here, say, like so. Or once again, at that point there, all of the energy E is potential energy U in blue. And then therefore, the kinetic energy K would be equal to 0. Notice that our coaster would be confined to this well, as we sometimes say, from here to here on this graph, when I give it this total amount of energy E. If I start the coaster here at this position, can it ever be over here somewhere on the graph or over here somewhere on the graph? The answer to that is no, those regions are unallowed, because, for example, in order for the coaster cart to get to this point here, the top of this second hill, the kinetic energy would have to be a negative number. So then therefore you would have right here in red the total energy E, and that would be equal then to the kinetic energy like so, which would be a negative number, plus, the kinetic energy like so, that is, which would be a negative number, plus the potential energy like so in blue, like so. So once again, if the total energy E is less than the potential energy U, then the kinetic energy K would have to be a negative number. So then therefore this region on the graph and then also this region on the graph is unallowed if I give my coaster this energy E and we start it right here at this position. Okay, now how is the graph actually related to the conservative force itself? Here's then how we describe that. Okay, once again, I'm just going to redraw the same graph here. Like so. Okay, and then ultimately this graph, potential energy as a function of R, is being described by a conservative force. If you're thinking about it in terms of a roller coaster, then of course it would just be the conservative force of gravity. Here's then how we begin to relate the conservative force of gravity to this graph. Okay, now the work done by the conservative force is ultimately equal to the following integral. Now, technically speaking, it is a dot product, it is a line integral, but let's say that the force itself is only a function of R for simplicity. That is to just directly relate it to this graph here. Okay, now if this is the work done by the force, then the negative of this is the work against the force. Like so, and then let's go ahead and take the negative sign and move it to the other side. Against, like so. And then recall that the work against the conservative force is the change in potential energy between any 2 points somewhere here on this graph. Like so. Okay, and then I can specifically relate the conservative force itself to this graph by not talking about this as an integral quantity over some broad time interval or over some broad 2 positions here on this graph, but instead talking about it in terms of an infinitesimal displacement. That is, in terms of an infinitesimal displacement dr. So let's go ahead and get rid of the integral sign. This then means that we write the expression like so. and then move the dr down to the other side. We'll also move the negative sign over as well, like so. Okay, now the reason why I went through all of this over the last couple of minutes here in this little derivation is now to specifically take a look at this right here, du dr. That's of course a derivative. But what is the derivative itself actually describing about this graph? Well, of course, it's the slope of the line tangent to the curve. So let me just pick a point here on the graph like so. Let's just pick that point. Let me go ahead and get a ruler for this. And then let me go ahead and draw out a tangent line like so. And then of course the slope of that red tangent line is described by this quantity here. But the value of the conservative force is the negative of that at this position. So then therefore, if the slope of this tangent line, for example, is a negative number, as you can see here on this graph, then the force itself would be a positive number. It would be a positive number in the sense of the distance r. So then therefore, at this position, the conservative force would act upon the object in this positive direction. That is, in terms of positive r. Therefore, if you position the object here, they would begin to fall downhill in this direction like so. This is actually a little bit easier now mathematically to picture, that instead of talking about this as a roller coaster as we're doing the conceptualizing, but now let's use a specific example that we've seen before, and that's a mass attached to a spring, specifically a horizontal simple harmonic oscillator. So let's do a little bit something that's more real world here, if you will, in terms of relating the math. Okay, so now a little bit more specific. A specific example. So just a horizontal SHO. So recall the details from earlier in this unit. Let's say, for example, we have a mass attached to a spring like so. Right here's the equilibrium position. Right here's the displacement x. And then the spring force, remember, always acts back towards the equilibrium position. The value of the spring force is described by Hooke's law as negative kx. Okay, now as we've seen earlier in this unit, spring potential energy, let me write it like this, is 1/2 kx squared. It's a function of the displacement x from the equilibrium position. Let's go ahead and graph out this potential energy function on a diagram. When we do, of course, we just form a parabola. Okay, now in this particular case, I'm going to go ahead and draw my parabola on both the negative side of the equilibrium position, we'll say, and the positive side of the equilibrium position like so. There's my parabola that's describing 1/2 kx squared. And now let's just examine the possible motions that could occur with some total energy E. So once again, I'll go ahead and draw a horizontal line here to represent a constant value of total energy E, and then we take a look at this position here on the graph. Right there at that position, all of the energy E is equal to the potential energy U in blue. Therefore, the kinetic energy K is equal to 0. And then you release the object, say, from here. And then down here at the bottom of the well, all of the kinetic energy is equal to the total energy E. And the reason for that is because the potential energy U in blue is equal to 0. And then you have the transformation of the kinetic energy back into potential energy on this side of the graph, like so. Once again, right here, the kinetic energy K is equal to 0 because the potential energy U in blue is equal to the total energy E in green. So if I give my oscillator this amount of energy, it is confined to this well. It oscillates back and forth, in other words, around the equilibrium position from this point here to this point here. This region here and this region here is unallowed because therefore you would need negative kinetic energy to be in those positions. Okay, now let's go ahead and differentiate this quantity. When we do, let's tack in a negative sign as well. And the reason for that is because this right here then gives us the value of the conservative force. So if you differentiate this, it ends up being minus kx like so, which of course is being described by Hooke's law. So once again, potential energy diagrams allow you to very quickly analyze the possible motions that could occur for an energy system. Okay, now let's go ahead and do a specific example. All right, I'm going to do some erasing here. Okay, so the specific example that we'll look at, I'll have you copy down into your notes in just a moment, is going to be modeling the following situation. So I have here two masses that are attached to a spring. We're going to think of each individual mass here as an oxygen atom. So here's an oxygen atom, and here's an oxygen atom, and then they're attached to each other by means of a chemical bond. In this case, they're going to form diatomic oxygen, which is O2, and the chemical bond that occurs between these two atoms is a covalent bond, where the electron shell is being shared by the two atoms. You could actually model a covalent bond for a diatomic molecule such as this as a spring, like so. We'll see that specifically in our example. Let me go ahead and read it to you here. Begin to copy it down into your notes. We'll break up this example into a series of small steps. Okay, so for a diatomic molecule such as O2, a model of the potential energy function for such a system is given as the following. Then we have this rather complicated looking function. Okay, let me copy it down. Like so. Okay, now R. As it says in the problem, the distance R is the distance between the two individual atoms. So it's basically from here to here in this simple model. And then you have these numbers A and B. The numbers A and B have to ultimately do with the electromagnetism that's causing this chemical bond. A and B, suffice it to say, are constants associated with that electromagnetism. The actual values themselves are unimportant for our purposes. But suffice it to say, A and B are just constants, simple as that. Okay, so what we're going to do is we're going to graph out this potential energy function. In order to do so, we're going to break this up, as I said, into a series of small steps. So let's take a look at part A. I need to move my file to do so. Okay, so this is going to be the first part of the graph that we'll construct. It says at what value of R is the potential energy U equal to 0? Okay, now mathematically all that we have to do is take this function here in part A of the problem, set it equal to 0. Like so. And now let's just go ahead and solve for R. So to do so, I'm going to move this term to the other side. Oops, equals, excuse me. There we go, like so. Now let's do some canceling. I can cancel out an R to the 6th here, and this then it becomes an R to the 6th, like so. Then let's take this R to the 6th and move it over to here, and the A and move it down here. Like so. And then to solve for R, I'll go ahead and do, I'll raise each side of the expression to the 1/6 power. Like so. Okay, now this point right here is going to help us begin to construct the graph. Let me go ahead and begin to graph out the function in the following way. Okay, for this particular example, we're going to need both a positive value and a negative value here for the vertical axis that's describing the potential energy as a function of R. And then what we found is specifically here along the R axis, what the value is equal to such that U is equal to 0. So let me go ahead and just draw that as a point right here. That point right there is the quantity that we just calculated of B over A to the 1/6 power. Okay, now we get to part B of the problem. Part B of the problem asks, or describe what happens to the potential energy as R approaches 0. Okay, so let's go ahead and let R go to 0. So if you let R go to 0 here in the function, notice that both of the terms, this term here and this term here, they basically blow up to infinity. However, is it positive infinity or is it negative infinity? Well, think of it like this. Notice that this right here is an R to the 12th and this right here is an R to the 6th. And now make the value of R smaller and smaller. Which number basically blows up towards infinity faster? The positive term or the negative term? The positive term does because of the R to the 12th as opposed to the R to the 6th. So then therefore the potential energy U blows up towards positive infinity for that reason. Conceptually this actually makes sense. Just kind of think of it like this. Once again we're thinking of this as a covalent bond. So now what I'm going to do is I'm going to compress the spring. So by compressing the spring, at least attempting to do so, what I'm doing here is I'm making the distance R smaller and smaller. I'm getting the atoms closer and closer together. It's increasingly harder and harder for me to do that. I basically have to do work against the electromagnetic forces that are causing all of this in order for me to press these atoms closer and closer together. Therefore, the potential energy increases, and it does so in this case as a positive number. So then therefore, the potential energy blows up towards positive infinity. Now, how does that help us on our graph? Well, basically what it means is this. Over here along the positive side of the axis, when r here gets smaller and smaller, the value of the potential energy increases towards infinity, like so here on the graph. So then therefore, as I begin to construct this graph, I'm starting to graph out a function that has to start on the graph by looking like this. And then it's going to cross the axis over here, and then something is going to happen over here on this side of the graph when r gets bigger and bigger. In other words, imagine taking the two atoms and separating them out from each other more and more. What happens to the potential energy then if you do so? That's the next part of the problem. So let me move the file. Okay, so now it says, describe u as r approaches infinity for part C. Okay, so now let's let r go to infinity. So if you let r go to infinity here and here, notice that both of the terms go to 0. However, from which side of the axis on the graph below, the positive side or the negative side, does the function approach 0 from? It has to approach it from the negative side because we already know that the function crosses the r-axis right here at this location, like so. So then therefore, as r gets bigger and bigger, my red function that I'm beginning to trace out has to then be approaching 0, like so, from the negative side. That is the negative side here of the u-axis. So once again, we can visualize this by going up to the function itself, making the value of r bigger and bigger. Both of the terms go to 0 as we do. However, we have to be approaching it from the negative side of the axis as I just drew, because we already know from earlier in part A of the problem that the function had crossed the r-axis. So then therefore, we can finish out the graph then as looking something like this. Now I'm going to kind of clean this portion of the graph up a little bit. I'm going to have it approach r a little bit more exponentially, like so, as the value of r increases. Conceptually, you can understand this portion of the graph in the following way. So take the two atoms and separate them from each other more and more, and then ultimately the force that's being exerted between the two atoms, which is electromagnetic in nature, gets weaker with distance. If you eventually take these two atoms and move them infinitely far apart from each other, then therefore the potential energy should be equal to 0 because neither atom is exerting a force upon the other. That's an easy way of thinking of it. Okay, and then the last portion here of the calculations that we have to perform is part D, and that's to find this minimum point right here on the graph. In order to do so, we'll take a derivative. Okay, so in part D, they're asking us specifically to find the derivative of the function above, set it equal to 0. That would mean that the slope of the tangent line right here is equal to 0. That is a point like so. So we're basically finding this minimum in this portion here of the exercise. Okay, once we find the derivative, then we'll just tack in a negative sign to describe the force itself that's occurring between the individual atoms. Okay, at any rate, however, let me go ahead to the top board and calculate the derivative. All right, so for part D here, I'm going to rewrite the function like this. Okay, now let me go ahead and differentiate it. Negative signs cancel. Like so. Okay, now let me go ahead and tack in a negative sign here for this portion of part D. And then this rather complicated, messy looking function here, like so. This right here describes the force that occurs between the individual atoms. Okay, how this models a spring, I'll get to a little bit later on in the problem, specifically when we get to part F of the example. Okay, so this is a portion of part D, writing out the force that occurs between the two atoms, but we still have to figure out where that minimum point is on the graph below. So let me go ahead and erase this now. And now to find that minimum point, let's go ahead and take the derivative and set it equal to 0. Okay, so cleaning this up a little bit, let's move this to the other side, like like so. And now let's go ahead and solve for r. So I'm going to cancel out an r to the 7th here, making this an r to the 6th, like so once again. Let's cross multiply the r to the 6th up here and the 6a down here. Okay, 12 divided by 6 is 2, and then we'll raise each side of the expression here to the 1/6 power. So then therefore the value of r in this case is this slightly bigger number than the value of r that we found earlier in part A of the problem for where the potential energy was equal to 0. Okay, so that point right there, this 2b over a to the 1/6 power, okay, that's basically this value right here where this minimum occurs. Like so, and that then completes the construction of this graph, okay? Okay, and then in the last portion of the problem, it asks us to describe the possible motions for this energy system for various values of total energy E. All right, so I'm going to pick 3 different values here of the total energy E. For the first value, let's go ahead and make the total energy E a negative number, and this will illustrate specifically why we can model a covalent bond as a spring attaching the 2 atoms, if you will. Okay, so right here is a total energy E, and it's a negative number. So notice that our atoms will be confined rather to this space on this graph. And then notice that here in red, this portion of the potential energy function looks like a parabola, which as we saw in an earlier example, of course, is modeling the spring force. So then therefore, if I give the atoms this total energy E, which is a negative number, then basically they would do something like this. They would vibrate back and forth more or less in simple harmonic motion, describing the exact same motions as we did earlier for the simple harmonic oscillator. Once again, right here is a parabola that's illustrating that. Okay, now let me go ahead and erase this negative number, and now instead let's make the energy E equal to 0. Okay, so let's get rid of this. Kind of clean up my graph a little bit. Like so. Okay, and then right here, let's make the total energy E equal to 0. And then let's just begin right here where all the potential energy in red is equal to the total energy E in green. The kinetic energy would be equal to 0. This region here on the graph is unallowed. So basically what we're doing here in this portion of the function is we're taking these guys and cramming them together like so, and then we're releasing them. And then basically what happens? Well, the easiest way to visualize what happens is actually go out to here when r is equal to infinity. When r is equal to infinity, the potential energy in red is equal to 0. Remember that this curve here is approaching 0 when r is equal to infinity. So then therefore, if the potential energy is equal to 0 at r equals infinity, and the total energy E is equal to 0, this then means that the kinetic energy is equal to 0. What we have done then, therefore, is we've taken this covalent bond and we've broken it apart, like so. So if we've broken the covalent bond, then technically speaking, mathematically, what happens is that the 2 atoms end up infinitely far away from each other, and they do so at speeds of 0. So we've broken the covalent bonds. Okay, then let's go ahead and get rid of this. Let me just make this blue again, like so. But now for the third case, let's go ahead and give the atoms a total energy E like so. That's a positive number. So then therefore, it's like we're cramming the spring together even more tightly than before. So right here, this portion of the graph, all of the energy E in green is potential energy U in red, and the kinetic energy is 0, and then we release the atoms. What then happens? Well, they're going to end up at r is equal to infinity, where the potential energy is equal to 0, but then therefore the kinetic energy would be the difference between the horizontal axis and the green line. In other words, once again, we've broken apart the molecule, but in this case, with this extra energy that I've given the molecule, well, we've broken apart the molecule, we've broken apart the covalent bond, and the 2 atoms then basically move off at constant speeds and straight lines forever. They would just obey the law of inertia at that point, okay? Okay, so once again, with a potential energy diagram and through the mathematics associated with it, you could very quickly and easily begin to describe the possible motions that could occur for an energy system.